Imagine sitting in front of a screen, staring at a problem involving deep learning, gradients, and multi-layered neural networks. For many learners, let's call our learner Arav, the first reaction is a sudden, almost physical weight. The terminology creates a dense fog, and the brain freezes before a single equation is even read. That paralysis stems from an emotional response rather than a failure of raw intelligence. When the brain encounters a massive block of unknown information, it prioritizes the perceived threat over the mathematical logic. Two psychological traps immediately take hold. First is internal resistance, a mental wall that claims the material is too difficult to even start. Second is the pressure of the clock, combined with the belief that everyone else understands the concepts instantly. In reality, most learners are likely just as confused, but the silence makes the isolation feel absolute. To break this cycle, a mentor might ask Arav a very specific question. Did the problem itself actually create your fear, or did your mind create an intimidating story about the problem? A machine can calculate billions of variables instantly, but the human mind requires hierarchy and sequence. To master artificial intelligence, we have to stop trying to fight the massive size of a problem all at once, and instead learn how to safely dismantle it. The tool we use to dismantle complexity is called first principles thinking. You can think of it as a mental chisel. We use it to carefully chip away the hype, the business buzzwords, and the narrative noise until we find the absolute, undeniable facts resting at the bottom. Our goal is to identify the real object. If you try to understand 50 concepts equally, your attention shatters. But every complex problem has a single tangible anchor point. Once found, everything naturally aligns around it. This core object reveals the underlying structure. Real-world scenarios, like predicting hospital readmissions, are just narratives covering a clean mathematical engine. We dismantle the story by asking the most basic questions possible. What specific data is this system observing? And what exact output, a number, a label, or a probability, is it trying to produce? True understanding comes from taking the chaos of reality and organizing it around one concrete, understandable mechanism, rather than processing a massive cloud of abstract information all at once. This scatterplot shows raw data forming 3 distinct color-coded clusters. To categorize this data, we don't start with complex code. We start with simple observation. Before calculations, we notice these data points clumping together indicate regularity. We are noticing a pattern before attempting math. Looking at this next diagram, we move up the ladder to decomposition. These orange dots represent specific characteristics of food. The blue dots are cars, and the green dots are birds. By assigning these labels, we've decomposed the abstraction into concrete, real-world objects. This text details how the system moves to representation. The machine draws a mathematical boundary, a simple line, to separate these mapped concepts from one another. After we observe, decompose, and represent, we arrive at computation. At this stage, the math operates as a sequence of small, honest steps taken to move a guess closer to the truth. Following this specific ladder prevents the brain from short-circuiting. Moving sequentially from observation to computation separates adaptable intelligence from fragile memorization. To move those guesses toward the truth, the machine relies on the loss function. In machine learning, loss is the measurement of error. The model makes a blind guess and then calculates the exact mathematical distance between that guess and the actual reality. This shrinking red line tells the system exactly how wrong it is, providing a strict direction for the next attempt. While a shame-driven human mind often tries to hide mistakes, a training machine mind treats a mistake purely as a location marker. Inside a neural network and your own head, errors serve as exact coordinates to update logic and move forward, rather than signals of failure. Looking back at Arav, the deep learning problem in front of him hasn't changed. The data is exactly the same. However, his mind has shifted from a state of floating anxiety into one of grounded, structured clarity. He is building the mindset of an AI generalist. This value resides in connecting domains, asking precise questions, and structuring complexity, rather than the rote memorization of specialized code. Artificial intelligence is a staggering tool for pattern recognition, but patterns alone are blind. They require human judgment, ethical review, and structural thinking to turn those patterns into something genuinely useful. Posing a direct challenge, the noise of the future is only going to get louder. When you encounter a system you don't understand, will you freeze and let the scale intimidate you, or will you look past the surface to find the underlying bones? The sheer size of an impossible problem is usually an illusion. Strip it down, find its structure. Walk the ladder of thinking step by step, and what once felt entirely overwhelming will quietly become clear.